before I do that, there's one thing that I don't know whether you get confused or not. Maybe I just ask you, whether you can explain it. So that's what I said last time. So if you have a function that define on a finite domain, so whatever variable x, you define a function is defined over a certain range of the domain, whatever you call it. Then you can do three kind of series. You can do the full sine and cosine series, right? You can do the Fourier sine series, or you can do the Fourier cosine series. Right. That's why I said that I just want to know whether you get confused about this concept, whether you get clear what does it mean. You have three series that you can do. So maybe I should say, so you can do a cosine, a full series. We have has both cosine term and sine term. But then you can also do a series only with cosine term, and you can do a series only with sine term. Can you explain why you can do that, or? You said, say that again. I didn't hear the first part. So you have like your sine. The cosine change sine is a phase shift, but so the full series are both cosine and sine. But now you can say that you can only use sine or you can only use cosine. Then why do you do the first series? First series has both sine and cosine. Why is it redundant? Is it redundant? You have both cosine and sine. But then you said that I said that you can do it only with cosine or you can do it only with sine. Can you explain why? Saying that splitting the function, whether it is even, if you have an even function. Yeah, but I mean, even all this is part of the argument that used to justify the formula. Basically, it's an imaginary thing you imagine. Say, first of all, we imagine that this is periodic, and then we use the series both sine and cosine. But even if it's not really periodic, we just imagine, we just copy the function just to the same distance of domain. Just basically copy this function here and there, right? But nothing. And then argue that we can do it the Fourier series. So it's not necessary. The function has to be periodic. Any function defined in a finite domain, you can do all these three series. So whether it's really symmetric or not symmetric doesn't matter. Even if it's not symmetric, you can do either sine or cosine series. That's fine. I'm just asking whether you get confused. You can explain why this is so. Anyone can explain, give a clear explanation?
Because if you just use cos or sine, they will give a harmonic, like a sine curve or a cos curve. So we need the curve is something else that is not harmonic. We need to use both sine and curve to produce a similar graph to that.
You mean it's not complete? So what I'm saying is all complete. All three series are complete. It doesn't matter. So given whatever f here, defined over this domain, all three series are complete. So you can either use any one of these three are fine. And like that's what I'm saying. So it seems confusing. So whether it's we use the argument of periodic function just to derive the formula. Actually, the function f defined over this domain doesn't really have to be periodic. You're just given a function over a finite domain, then you can do Fourier series. Yeah, just the argument for argument's sake. That's for convenience. That's for later how you choose which series to use. but all three series are complete over this domain. So okay, let me use. I mean, it's more apparent if you fix the domain for the all three series. So for 0 to L, right? Because when we first divide the for Fourier series, cosine and sine, we call the period 2L. So either 0 to L or minus L to L. We divide the formula. So if you change to 0 to L, that's fine. We scale everything. So the original formula, you can look that up without dividing that. Last time we do it, we divide that by rescaling, and you can just copy the formula. This is 19.10. So for if the period is 2L, then f it to a 0 to a sum of n cosine term and pi of L. That's the sine term. And then all the coefficients are. This is for the period 2L. So you either integrate from minus L to L or 0 to 2L. Let's just write 0 to 2L. Okay, so this is the original one with the period as 2L. But now I change my mind. I call 0 to L instead of 0 to 2L. All you need to do is just rescaling your variable, right? Or you can simply say that's whatever the period, instead of calling it L, you call it 2L. So the old L becomes the new L over 2, right? Right. So whatever you have L in the old formula, just to get to the new L, you just divide it by 2, right? Can you follow the argument? So this formula becomes this L, becomes L over 2. So you have 2 here. You change it to factor 2. And all these formulas you also change. So, so this is L, change to L over 2. Because you can just integrate from 0 to L, right? And then just change the L over 2, over 2. Okay, then you fix the formula. Right? That's if you're expanding a function f using the Fourier series, full Fourier series with cosine and sine. These are the formula of 0 to L. And they're periodic in the sense that when you change set x equals to L, you get to n pi. It's to n pi, so they're all periodic over the period. Okay, so that's the full Fourier series. But then I said that we can do the sine series and cosine series over the same domain. Now you write the cosine series. I should not use A because I already use A. Like whatever you use, C0 over Q, and then n from 1 to infinity. And now the difference is here. For the cosine series, you still use the old one because the cosine series, you imagine you copy that to the other side and make it symmetric. So then you use the formula with the period equals to 2L. So you go back to the old formula. And likewise, all the C's ends are using the old formula. Uh, I should say that using old form, but with the period over minus L to L. So you do it this way. You integrate from 0 to L, you just get half of that. So you need to multiply by 2. Okay, but this is still different from that. So the coefficient is the same, but this is n pi x. Okay, and likewise, you can also do the sine series. No, it's d sub n. What the d sub n and like the same way. Okay. So now do you see the difference? So there's 3 series: the full cosine and sine series, the cosine series and sine series. Now can you see very apparent, right? The 3 series are different in a major way. What are the major difference between like the cosine series and the full series? What is different? What is the major difference?
You're taking both, it's from minus L.
Minus, I don't have minus. N equal 1 is both are n equal 1 to infinity. N equal 1. What is different? Yeah, this is cosine 2 n pi x. This is cosine n pi x. You see that? What does it mean?
That's just the half the distance.
Yeah, that's the half. That's the half, but not. So this is all the integer multiple by n x over L. Right? All the integers. So n is 1, 2, 3. But this is not. This is 2n pi x over L. So it's just sum over all even integer in this case. Right? All the even integer multiplied by pi x over L. This is all integer. Okay. So you skip some of the modes in here. Some of the cosine term in here is not in here because you skip all the odd n. All the odd n terms are not in here. Likewise, all the odd n term in the sine series is not in here because you have 2n pi x. This is n pi x. Right? So ultimately, they would all 3 are complete, but they are I mean they are infinitely they are infinitely many number of bases, but some of the bases in the sine and cosine series are not in here. They're not in the, you basically skip over one another. So, right? So essentially, you can say that you have the same number of bases, although it's infinite. But because you have both cosine and sine, but either one of these only have cosine or only have sine. But they have kind of more modes in the sense that there are some modes that are not in the original one. Basically, you keep all the integer, but this is all the even integer. Okay, so that's it. Okay for everyone. So that's sometimes it cause confusion even for people that use Fourier series a lot. They like when you do numerical calculation, you can either use Fourier the usual Fourier series routine. The fast Fourier transform usually is written in a full series, but there's also sometimes provide you the cosine transform or sine transform. I mean, you can use all of that to do calculation. The only thing different is that some series are more suitable for some application than the other. It's just maybe the number of terms will be smaller, like what I mentioned that this term satisfy obviously satisfy the boundary condition that at x equals 0 L is automatically 0. So that make it convenient, more convenient. If the function is 0 at both n, use sine series is easier. At least there's no apparent discontinuity at the boundary. But if you use cosine series, then yeah, you need to get the constraint over the sum over n at the boundary and make it difficult. Or vice versa, if this is non-zero, if f is actually non-zero at the 0 or n, if you use sine series, you can still expand that although not right at the boundary. Right at the boundary is 0, obviously. So basically, if you use enough term, you can all the summation approximate this f quite nicely over the whole range when it's smooth, but it drop quite fast to the 0 if you use a sine series to do the expansion. So it cannot expand the boundary term 0. But the interior, you use sine series, you can still do that. Okay, that's some subtlety that you might not, we sometimes get confused.